So if you're just tuning in, so basically this has been the buildup, and it's we're at application phase now as far as implementing generative AI and other emerging tech into specific workflows. So what we see here is basically, so this is speed ups for state-of-the-art generative AI drug discovery. And so this is Wednesday, July 3rd. My name is Kevin Kocek. I'm the founder CEO of Chemical Q Device for discussion 142 with this. So the first thing is we're going to go through some papers. So the first two are basically their reviews, and very helpful. I actually saw from a different colleague on the second one. The first one I was more aware of, and I had time to read through both of these today. And it's going to highlight in specific all the different types of GenAI. Like I've mostly been covering large language models and large multimodal models. This gets into variational autoencoders, GANs, normalized flow. Those are the first two. And then C here is unique because it's a real research paper based on their specific type of model that they're trying to share with the world here. And then we're going to end with speed ups for this. So, you know, it's not an industry that's basically set in stone yet. I would say is it's basically here to there. You know, things are still on the quality side and the speed side, you know, things are getting worked out. So this first paper here, so if you haven't seen this one before, it's by Gangwal et al. And it's a drug discovery today paper. And basically, here we go. It's a really good overview, and I find it like very current as far as saying, like in this specific case, you know, people are using you know, this type of generative AI. So again, this goes very deep with generative adversarial networks, and kind of the newer model to the block is basically it's diffusion. So you'll see stable diffusion, stability AI, those types of things. And so here's an example of using deep reinforcement learning, you know, with the drug discovery process. So some things with this is basically we can theoretically access this entire drug-like space with novel structures, you know, with desired physical, chemical, and biological properties. And these deep generative models, which is a blanket term, and generative AI in drug discovery was used far before models became deep, you know, so figure larger models in size, increased function, stuff like that. And basically, in some things, it's still trying to, you know, get situated with chemistry rules. And the ultimate success is basically a lot of times going to be the wet lab results. So we get these compounds and then they get tested in the laboratory somewhere. Okay. And so and they say this model practical utility depends on a nuanced understanding of you know, capabilities, limitations in the broader ecosystem. There's a call to establish more comprehensive molecular databases. Right now, there's, you know, so for every big pharma company, they've got their own data. You know, there's efforts. I think in the UK, they had something like that where they were able to get some type of collaboration between different, you know, databases between organizations. So figure the public ones, maybe not as good as the private databases that your leading pharmaceutical companies have. And ever since, you know, about 2017, and you can track this with other FDA kind of approved, you know, deep learning algorithms, say maybe 2019, I think it was Arteris with deep learning. So basically, deep learning, more computation, more utility, takes more space, but as computation improves too, it can run it. It's not as small and it's more powerful than the previous non-deep technologies. And since 2017, pharmaceutical companies have partnered with AI startups, academia, to start to make this push towards more generative AI, you know, stronger types of machine learning, basically. So the second paper here is basically it's machine learning aided generative molecular design. So a more specific aspect of drug discovery is they call molecular design, so or like chemical design using generative AI properties, those types of things. And, you know, so we see in this specific one, you know, these are basically 6 molecules that were, it says selected examples of experimentally validated generative designs. So again, building molecules from scratch, de novo a lot of the times. And the top three are distribution learning, and the bottom three, it's a different type called goal-oriented generation. So these are examples of good compounds, and it's still a work in progress as far as every piece kind of has to be correct for it to really take off in industry. And so basically with this one, it has provided a means to accelerate early stage drug discovery. So we're at that level of like 10,000 compounds here. And interpretability is key, because if you have a chain of events that use generative AI, it helps after every step to be able to tell why it did. And we have some level of control using services like Langsmith, because it'll actually explain all the details in full, as opposed to just reading a generation from a notebook. But a lot of times this is associated with having to use different software architectures like tensor networks in order to, at every single step, be able to explain things more and more. So conformational dynamics, the role of water and entropic contributions are often overlooked. So water plays a huge role. Water's everywhere, in the body. And so the next steps, and this is where chemical Q device comes in, is with large language models, large multimodal models, to revolutionize molecular design with text-guided discovery. So again, figure like if you want to type in a sentence or two as a prompt, that's maybe a better starting point. And there's already papers, one's called ChemCrow, where you can actually, it's chem and then CROW. You can type in a prompt and it'll actually, GPT-4, some variation of that, will produce the reaction conditions, and then a robot in that specific paper, actually made it in lab, and robotically. And you'll see these types of things improve. So when they say increasing demand for high throughput self-driving labs, that's automation, that's AI to expedite this process. And I think a lot of times, this is where the industry is going, with higher technology and moving beyond, a lot of these are more for smaller molecules to proteins, which are chains of amino acids, or polysaccharides, which are chains of sugar molecules or carbohydrates, that's likely coming too. So on this specific thing, okay. Self-driving. Okay, so this is a specific research paper, and it's 2024, and it's kind of like that step forward. Like when reviews, they're not going to go over methods, they're not going to go over like the specific details that specific papers would, just like here. So it's called Deep Representation Learning of Chemical Induced Transcription Profile for Phenotype-Based Drug Discovery. And it's by this Tong et al., Nature Communications, and they call this a transigen. It's basically a variational autoencoder. And, tying in with the discussion right now is the size of your machine learning model, or your deep generative model, will a lot of times, that's how fast you can go as far as speed and processing data. But in general, this is a brief overview. This is in supplementary that I got this from. So the next one is basically this. So transigen, so this is the authors here, this Tong et al. This year. Transcriptional signatures generator analyzes basal cell gene expression and molecular structures to reconstruct chemical induced profiles with high accuracy. So it's a self-supervised, that's different from unsupervised. And in these papers, especially the reviews, those two that I just had mentioned, it's a far greater number of different types of generative AI, being used in applications than as you see like with these leading models that I access through Hugging Face and others. And again, that type of generative AI is moving more towards the drug discovery applications here too. And they say, it's instead of genotype, it's phenotype-based strategies, expands the range of compounds that can be screened with predicted perturbation profiles. And they tested it against 4 other types of models, this LEPs, and then 3 other ones. And they said that theirs was the fastest out of these other 4 models. Okay, so that was papers. And then, so we're going to move on to Hugging Face pipelines. Now, if you're new to generative AI, this is the type of notebook you should run. I literally find these pipelines all over the web. They're on Hugging Face. They're on model cards, or the actual models. A lot of times it'll say, run this quick piece of code to test the software in some Colab notebook or your VS Code or whatever, or Jupyter notebook. And so I put them all together. Now, the reason why I did this is because they're really important to see all the different types of functions generative AI can do. And in specific, like the one at the bottom, so it says video classification and the model, you can, instead of doing, that's one of the 32, okay? So there's text generation, there's other types too. And the model themselves, if it says video classification, here, you click on video classification on Hugging Face, and then you find all the leading models, and then you can experiment with this. So thinking outside the box, and anytime you're trying to apply a technology to a specific field, is you really need to experiment with a bunch of different ways of using generative AI. And I'll give you a hint with this, is that ChatGPT 4.0 can do many of these tasks. I think they turned off the video features because probably of bandwidth, but it can do a lot of the 32. And it's an exciting thing, because I went through and I said, fill in the blank, which is not it's called a fill mask. And it actually does that, somebody's blank into home plate, in a baseball game, and it just right away said slid, right? But that's a proprietary model. It's up in the cloud. We can't see what's going on with it. And if we only want specific functionality, i.e. a much smaller models that potentially could run on local hardware privately, with medical data, then we're talking about, these types of functionality that are, this is really important. So they say pipelines allow for speed, simplicity, and screening of many deep learning workflows with minimal code. So some of these you can run at like 4 or 6 lines of code to further incorporate into specific workflows. So say like everybody else in the industry is doing text generation, and LLMs. And then in drug discovery, they're using variational autoencoders or diffusion models or, GANs and these types of things. Then how else can you think beyond, simply saying, I want to have a large language model, I can do speech to text, and then it'll just create my whole experiment for me and do everything. Well, that probably is going to be for a while, right? That's not going to be now. But I think that you get the idea with this, is that this type of GenAI function is not limited to many people's traditional approach in thinking about the technology of just solely conversating with ChatGPT or Gemini or Meta.ai, and I'll get to Groq here too. So there's all these different functionalities, and it's a good thing too, because if they're specific models, they're not nearly as big as these huge proprietary models that are actually, optimized for speed a little bit with, for inferencing. But this one allows you to fine tune. So this notebook is up on the cloud. And again, I tested it with rich text format. So when it said specific, like look at a document, question answering document, and then for audio, I put up an MP3 file. You'll have to do that with your own, okay? And then a ping file, like an image file. But it's a great place to start. And I think it's for experienced expert users of generative AI to get outside that box of saying, like, this is the traditional way. This is the only way of doing drug discovery, for specific applications. Now, the next one is basically using C++. So a lot of times you have a PyTorch model, or it's, Python, these types of things, and you convert to C++ in order to get better inference on it. And I've experimented definitely with the Llama.cpp. Some of these other ones, TensorRT, I think there's a paywall somewhere in there, but basically with Llama.cpp, you can use a specific compression methods, okay? So when we're talking about generative AI, in order to get to run on an iPhone, like I can run Llama 3, 8 billion on a, just barely on if it's a compressed version, like 4 to 6 gigabytes on an iPhone. Now on an iPad, I can run more because I have more RAM, right? So it's RAM. So figure for the model size that plan on that having to occupy the RAM in that device. So in Llama.cpp, you're in C++ and you can compress past, you'll see 4-bit 16-bit float is like full, you know, and then you'll see 4-bit, which is a compression, and they say all the way down to 1.5. And what this does is you have specific parameters or weights in machine learning. So instead of this weight saying 1, 2, 3, 4, 5 dot 1, 2, 3, 4, 5, 6, 7, it truncates the however, you know, if it's going into an integer, it's going to truncate the decimal points that's making that a float. And they use Apple Silicon Metal frameworks and, you know, NVIDIA CUDA kernels as well. Now with TensorRT, it seems like NVIDIA, like they have multiple things figured out all across from GPUs to healthcare to, you know, running fast inference like this. So they say up to 36 times faster than CPU only using a lot of the C++. They call it layer and tensor fusion. And then TensorRT large language model optimization and 6 times faster, you know, inference versus just using PyTorch or TensorFlow alone. So again, these are typically production ready models. You know, these aren't, you know, you typically come up with your model using Python, PyTorch, or Python TensorFlow, or some combination of those. And, you know, so we see with LibTorch, which is the C++ version of PyTorch, high-level pure C++ modeling, just-in-time compiler, and then the C++ extensions for Python use, and auto multi-GPU parallelization for that one. Now, the thing that excites me a lot is this Groq Cloud. So there's 2 Groqs, okay? So Groq is, you know, XAIs, you know, like Tesla, and that's the 340 whatever billion parameter model. Now, Groq Cloud is basically, it's using, you know, basically lightning fast inference in the cloud, and you can go to Groq.com, or you can go to Groq Cloud, get an API key, which is what I did, and I ran these sets of experiments, okay? And this didn't take me too long to do. So they have 4 text generator models, these large language models. So I used Gemma, 7 billion. They actually have a newer version of Gemma, but it didn't seem to hurt in this specific case. Mistral, it's called a mixture of experts, which is 56 billion parameters, which ran probably faster than I thought. There's Meta Llama 3, 8 billion, which is like a de facto standard in the industry right now. And there's Meta Llama 3, 70 billion. Now, I asked Groq, you know, what exact models these are. I know they get them from Hugging Face, but they're probably a quantized version, maybe a Q4. And I know they have some significant hardware servers running these. So when I generated this question, is basically I asked it, what is the best generative AI technology for molecular design? And of course, each of them had their own different, you know, generations or outputs. So the Gemma was actually the shortest at 267 words, Mistral at 311, Meta 8 billion, 495, and then, you know, also with the 70 billion at 548. So it's an approximate, and it can be skewed based on how long your words are, but it's approximately 1.3 tokens per words. And a token is a numerical representation of a word that is used by the large language models. So you hear that type of thing. It's separate. This word token is used in, you know, Hugging Face token ID. That's like an API call. It's separate from that. It's specifically relating, turning words into a usable format for generative AI to use. Now, a lot of times I would run these and I'd be like, I'm familiar with the subject. And I thought by myself, maybe Gemma was first. But what I did is basically I put this up on GitHub, so you have access to it too, is I took each of these and I assigned them numbers. So I called Gemma 1, 2, 3, 4, all the way down to Meta Llama 70B. And then I copied and pasted the generations of those. And I asked each of the judges, without telling it which model was which generation had the highest quality. Okay. Yeah, is the highest quality to the following question, the original prompt. Now, ChatGPT 4.0 can do a lot, you know, as far as images and audio files. And, you know, this is asking it to be a judge of 4 different answers here. And it handled it very well. And you can see on the GitHub, you know, I'll put it up there, but we're talking about our proprietary model. I pay $20 a month for ChatGPT, and I pay about $20 for Gemini too. Now, the thing with Gemini is it's actually, Gemini uses Gemma. So if anything, it might favor Gemma because it's used to that architecture and like the answers that it produces, but it was my second best. I couldn't get my own models to be good judges of the 4 other answers that I have with Llama, and going up to like 7-8 billion parameters. So Mistral, so with the Mistral one, ChatGPT favored it the least, and then number 2 with Gemini.google, and Gemini.google is very similar to ChatGPT. It's a little bit flashier, but the thing with Gemini is you cannot use human pictures as of yesterday. So if you want to generate a human picture, if you want to upload a human picture and ask it to say what's in this one, it says it just can't do humans. So I'm assuming that might be a temporary thing, but I don't know. So this other one with the 8 billion, it basically was, out of all these with a Llama 3 8 billion, which is like a de facto standard, it was performed the worst according to both judges, but it was also the fastest. So 983 tokens per second, and we're talking about speed here, is I can only get about 50 tokens per second using my Llama 3 8 billion. And again, I don't know exactly what version they use. But if it's the full one, if it's the 16 gigabyte model, it's even greater. So the last one was this Llama 3 70 billion. So I'd say that's the number 2 based on these responses. Now, what's interesting about this is obviously Google does a lot with healthcare, and this is definitely a question kind of up their alley. And it won this competition based on the output, right? So a prompt is me, I'm the user, I type in whatever, and then the output is the answer or the generation. And we see with speed, the first 2, maybe Gemma was a little bit slow based on 7 billion parameters, and I checked the Hugging Face and it is a little big on the model size. And then this mixture of experts may be a little bit fast for what it was. And these are single generations. So if I went back and did the study again, and I did like 10, 10 of each, it might vary a little bit. And then, as mentioned before, the 8 billion parameter model at 983, and then the 70 billion parameter, which is by far the biggest out of here, at 413. Now, as it compares to the website, I was a little bit slower. So they're at like 1200. So when I type into Groq.com, and basically when I use this, so here's the website. And this is different from Groq Cloud, which I used in the, the specific, let's see here, study, but I type in, the same question. And here, but it should be using pretty similar hardware and software approaches. So I type in here, and we'll see how fast it is. I just go click, or it actually wants me to sign in. Pick this one. So, and let's do that again. So click, and so pretty fast. So 1254. So it's approximate. So if you divide that by 1.3, somewhere around 1,000 words in a second, this specific, speed is what we're talking about today, is what it can do. And as you saw there, is I can also do the 70 billion, and then I go paste. And this one's a little bit different. So it actually adds, it adds the answers to the top, not the bottom. And then it doesn't save the chat. So every time you log off, it's gone. So with the 70 billion parameter model, that's at 350 tokens per second, around 300 words per second. And the other stuff is basically, if I go to Groq Cloud, which is where I did all of the experiments, is I can set the temperature, so it'll kind of like, kind of relax and, give kind of more explanations with higher temperature. And you get your API key. Well, first, these are the models. And again, the model cards point to Hugging Face, right? So the base models should be pretty similar, and I'm not sure how much they compress them off that. And you can get this text. So one of these worked. I wasn't able to get these two here. And of course, if you're using Python, you use Python. But I have the notebook up on GitHub. Now, the API keys this is what I use, and it's not going to show the key because I took it out. And you can add keys or remove keys. And settings. So here's the really cool part. So all of these are about 10 times cheaper than like OpenAI. So again, they're just base models. It's not something like, super high utility. We're talking about super high speed here, but 59 cents and 79 cents. I think that's like, per million tokens, that would be like $5, right, on OpenAI. And it's still in development. But again, I haven't found anything quite this fast. And actually, if I go to some of these other ones, these are saying how much it would be if I were to get charged. And it's a very small fraction of a penny. So that's like 0.1 cents right there for Llama B 70 billion, which is even, bigger model. And then these are like just a very small fraction of a penny per usage. And so if I go to chat, it's just the functionality is like you can upload all this type of stuff. And if I type in the same type of thing, and again, I use this ChatGPT 4.0 as my judge. And, so occasionally we'll just go to new chat. So and I'm not sure, so they can actually slow this down to make it easier to read. So like every response is similar, but we could see this is generating probably under 50 tokens per second as it's shown on the screen. But it typically gives the highest generation. Like it acted as a judge very well. So when I go over to GitHub and then into here, I'll show you the code. And this is the ChatGPT response. So we're gonna zoom in there. So actually, I'll start here. So this is what I gave ChatGPT and Gemini. So I said, rank and order these 1, 2, 3, 4 based on this prompt. Okay. And then so ChatGPT 4.0 was the first one. Now this has good utility because I've seen software programs that you can pay for these types of things. And if it's your prerogative, you can. But in theory, if you have a good working model like ChatGPT 4.0, that it knows how to act as a judge and it doesn't get confused. And of course, a very small model wouldn't have the context to do this. So I was happy with this because it actually ranked it. Now, when I asked the Gemini to be the judge, it definitely said that first one, although it was Gemma, which Gemini is made of Gemma, but I didn't tell it that, is it said 1, and then it kind of grouped 3 and 2 and 4 together, and then the last one. So not as definitive as that ChatGPT. Okay. So again, these haven't been run 10 times. This is like a, going through the motions of these 4 different models there. Okay. So we see that with all these, and let's see, participants. And if anybody has any questions or comments, then we could do chat now too.
So, Kevin, you once again compiled a whole bunch of information about these various models. Have you been keeping track of what they're trained on, if they are focused for particular tasks, for example, or are they just all just generic, trained on everything on the internet type of things?
Yeah, you can get like just starting with Meta Llama 3. So it'll tell you like how well it does in these scores. And say, for instance, it was trained on like, so this is the original training. This is the expensive part. Like it may be more expensive to run a bunch of inference or kind of like, prompts at the end. But basically you could see that it does well on these college courses and like chemistry and math and medicine and these types of things. So as a researcher, you have to be aware of that, because if you think that if you're using RAG or retrieval augmented generation and you're pointing to your document, you also want to make sure that the model doesn't know it and that your research is valid, right? So that's the thing, is that you know, they say only 5% of the world's data is public, and that's still a huge amount. And a lot of it's, you know, stored locally or these types of things. But just in general, it seems like the corpus is getting larger. So I think Llama 3 was trained on 13 trillion tokens. So that's approximately 10 trillion words. And that can span anywhere from papers to, you know, exams. And they've already passed law exams and, you know, these types of things too. So the only way to be super sure is to train on your own. And you have some architecture like Llama 3. And I think it's going to be more involved in fine tuning, basically adding some parameters in addition to the large, you know, corpus. So I know right now, you know, like say, for instance, Multiverse is doing that with their own tensor networks to try to get explainability and I believe similar types of, or if not better types of performance with 2024 models. But yeah, that's generally the thing, is that you don't know exactly, and these models dream at that same time. So even if it's trained on 13 trillion tokens, it's in specific directories. I find if I can point to it in specific, even though the main Llama model was trained off of that, it's probably not going to know all the specifics because it's done in a compressed way.
So do they like even publish, like they say, oh, this model is trained, you know, somewhat exclusively on academic textbooks published in vetted knowledge, or is it just whatever went by on the internet
Well, the one
for the
thing that we
last
don't
4
have,
years?
yeah, the one thing we don't have access to in Llama 3 is the training data. And
Yeah.
we can actually, you know, find the benchmark scores. And if it's passing all these, you know, flying colors in math and physics and chemistry and stuff like that, I think it's probably safe to say that it was trained on, you know, some of these maybe standardized tests and those types of things. But yeah, a lot of times the issue with training on your own is it would be almost for many people that aren't experts to try to replicate Llama 3, the results after they trained on theirs, even if they say this is exactly what we trained on, it's going to be different. Even if you had that same exact training set based on other machine learning parameters, you know, the GPU, you know, the hardware too.
Okay.
Yeah. So it's a type of thing. It's like, you know, some things we have to glean, you know, we don't have 100% information all the time. And if I were to hazard a guess, I have come across models where they say, again, like with Multiverse, where they say because they don't have access to Llama and they did it Llama 2 at that time, all of the data. And then they'll do the Llama 2 architecture and then their Llama 2 modified architecture on the same data sets. And then you compare the results between the two, like as a, you know, a decent way of doing like like comparisons. So yeah, this will be up on YouTube. It's Chemical Q Device, and I'll put it in the chat. And then, so the other thing, if anybody has any other questions here too, immersion utilize quantum annealer. So as far as other types of technology, what that wasn't in my scope this week. Now with drug discovery, especially with early phases, you're going to have more leniency towards other methods that say like have some type of noise that you can't get rid of. And I would say the preference right now, you know, is definitely trying to get standardized data sets that everybody can use, you know, across industries as opposed to just each big pharma company having their own. But yeah, explainability is a big thing too. So if you're designing things, you know, kind of from the ground up, that's, you know, that's a huge thing. And by that, I mean interpretability or say like, you know, at every specific step, can you see how the GenAI model got the answer? And right now we have some other tools like Langsmith to actually check, and we can check in detail as far as what it was searching. And we can actually sense if it was a poor generation, we can redo it, right? So then the next steps with that, with other types of technology would be, you know, using more, they're called linear, you know, types of processing as opposed to like neural networks and fully connected layers that are nonlinear. Like it's harder to tell, even though they do a good job at like long range interactions between data. So yeah, and these types of, like I said, there was a question in the chat. I think it's more open to use other types of technology that say, have issues with noise, but say high dimension. Now, that can do high dimensions easier. And what was in the chat is basically a specific type of annealing. So, it just depends. But this whole thing with chemistry and chemicals, it's a very high dimensional space. So in that first one, variational autoencoders are synonymous with dimension reduction into a latent space, and then you go back into some higher dimension. But it deals well with noisy data, that type of stuff. Like real world, you'll see a lot of variational autoencoders, for instance. And yeah, I think it's just the door's a lot more wide open. So if you have some other GenAI application that's, a diagnostic, and then you're relying on this for somebody's like the outcome of their health, those types of things are going to go through a lot more checks. But I think for the most part, and what I found is that the diversity in different GenAI software is much greater than what I've been encountering working on all these different frameworks, mostly with LLMs and LMMs. So, and some of them have been around a while, and GANs a lot of times now is being replaced by diffusion models, so stable diffusion, those types of things too. But when I put together this presentation, I really wanted to think outside the box, especially with Hugging Face pipelines, and say like, okay, so the rest of I just read 2 reviews, right? So the rest of the world is doing their drug discovery, molecular generative AI, this specific way. Do you want to follow them exactly, or do you want to learn from that and then also implement other things that can work too? But I think what you'll find a lot of times in literature is it's the technologies that work well with the data, like variational autoencoders work well with denoising, data. And if you have like an image that says 7, and this is just an example that has a noisy background, it can, basically convert that into a certain latent space, and then also, say 7, but train it so it just says 7, but without the noise, right? So that's what you're talking about. But if it's something simple as saying like, if you're talking into your iPad or your iPhone or the MacBook or your Android device, and you speech to text, and you could do it really fast, that could be an application there too, right? And as opposed to typing everything in. And in summary, in this specific part, I'd say that because it's early drug discovery right now, are looking at all these compounds to start off with your best 10,000, is that there's a lot more, I think, openness as far as using a broader range of technologies like GenAI or other technologies here too.
So Kevin, 2 weeks ago in Boston, I saw an amazing presentation. I believe it was by Polaris on their current track in drug discovery. And I know there's different types of drug discovery, but they're now focused on figuring out how to synthesize specific proteins to plug into like receptors on damaged cells or something like that. Well, these proteins inevitably become hundreds of molecules long, so it becomes a computationally intractable problem. So their approach was they're using a quantum annealer to figure out where to break those proteins, and then once they do that, then they hand the fragments off to the LLM, and the LLM predicts whether those fragments can be synthesized, and then the final step is to see if there's another LLM that predicts whether the fragments can be strung back together to get the final result. And their response was they've given up on just LLMs alone. They've tested this against all of the ones you've mentioned here and and some other ones, and the performance improvement. And again, the quantum is only on the front end. It's not part of the LLM cycle per se, but it's just allowing you to do like a 50 of 100 choice thing very quickly, and with an objective function, you can easily pull out the best candidates to feed to the LLMs, and they couldn't be more happy with what's going on. Again, they're using real quantum annealers because they're way beyond simulators. The quantum annealers that I've worked with can handle 5,000 constraints now, and they're definitely showing progress. And I know when you talk about quantum and gate-based stuff, noise is an issue. Well, in annealers, noise is how the thing works. It's the noise that shakes out the result and gets you the answer you're looking for.
Yeah,
So it's very exciting.
I think the biggest thing is like there's so many steps, so welcome technologies would be ones that are more explainable, like tensor networks. They're practical, they're cheap, these types of things. And you can take high dimensions, convert it to low dimensions, and it just does that naturally. But the harder part is to keep the performance with these types of techs. Now, the thing I would like to say is my learning lesson with all this stuff is that I passed through other types of tech to get to this point with GenAI. Is I'm still likely going to be utilizing this other type of technology, but you have to ask yourself the question, like, how many different platforms support that technology? And if you're passing through all these, previous ones where I was just had like one or two, and it was just like, we had a hunch, or maybe we have an algorithm and those types of things. But with Gen AI, it's a massive community. So even if you were just to focus solely on a framework like LangChain with Langsmith, and then using Llama private, on the computer, it works. I have 15 models I can share, I can host, these types of things. It's just that's my experience, is that it's very hard to break through unless, like, if you're just one of the few, right, just using that technology, and there's not many manufacturers on the hardware and the software side, it's just going to be excruciatingly hard. And I'll give an example, like with generative AI and drug discovery. As you read these papers, it had to go through regular generative AI, right? So before it hit deep generative AI, these deep generative models, is that, it took many, many steps, these iterations to get to these points. And the chances of just getting lucky with like some other, type of technology that's not well supported, it's emerging, right? And things could happen. But as any other type of startup, I think that's a very hard proposition. And like I said, I think the in-between right now is like the tensor networks, because they're all CPU, GPU, they're quantum inspired. And, so basically you get that just like how our cells in our body are quantum inspired, but we're only using the parts that are necessary to get the speed, to keep speed, and to get the performance of this quantum mechanical world inside of us. So, and tensor networks, like there's iTensor, there's 10Pi, there's some other ones too that you can do just inside of PyTorch, those types of things. But it's not a big thing yet, right? It's still a lot of R&D. And, so basically, if you're looking to make it as some startup, you have to ask yourself that question, is like, does it support you, even if there's only like just a handful of other companies, the results aren't in yet? And you have to convert between, different types of like classical data to quantum data, these types of things. And I've heard it mentioned too, in these papers, they say agentic workflows. And, as far as being with the LLMs, coming into, molecular design as a more mainstay kind of thing. And there's more flexibility because it's just to get these compounds. It's not actually yet to say this is a definitive answer, on this specific person. But that's the biggest learning lesson that I learned with all this, before you really spend a lot of time and energy and money to develop, is how many other people are in this. And yes, you could have a chance of breaking through, but if the results aren't awesome and it's not across the board, and like these two are just two of the, deep generative model papers out there for generative AI, and, there's likely many others as well. So, that's just my experience, is you have extremely complex technology, but something like the next steps is, now going through and applying LLMs and making it easier, and then, doing agentic workflows and applying RAG and Raptor and these types of things that are synonymous with GenAI. I think it's a lot safer to do that. And I think that your chances of kind of like panning out are a lot greater if the whole community is big. And for the first time, the iPhone rollout, Android phone rollout this fall with GenAI 2 is an increasingly accepted technology, and a very there's lots of different utilities like with Hugging Face pipelines. So from a commercial aspect, I think those are very important principles. Like anytime you study a new technology and you go to do an application, you really have to understand who else is in the market. I think it's a lot better, a safer bet for an overcrowded market. Maybe Gen AI is considered that, but at least the tools are in place to get the really good results. And you can, like I said, implement these other technologies too into today's, what we're seeing in reviews that was done, in the past couple of years. So,
well, the beauty of quantum optimization on the front end is it reduces your LLM workflow, and everybody is looking for that because generative AI is running into a brick wall in sustainability. They had some numbers posted on what Chat 4.0 was trained on, and they did some basic calculations on how much electricity it took. It turns out they could run something like the whole state of Rhode Island for a year on the electricity they used to train that model.
yeah, in any new
So
tech,
there's people
maybe, but
looking for ways to make these more efficient, and they've demonstrated that if you optimize on the front end, you still use everything you know about LLMs. You definitely get better results. And it's not just one company or one entity. This is happening across the board. And people not, I mean, Polaris was a startup at one point, but there's other companies that are starting up and they're getting the same results. So I mean, you really should look at. I mean, it right now everybody's putting their bets on the combination of the two. And you were talking about being able to explain things. Well, the mathematics behind the optimization stuff, it's just all binary quadratics. It's even way more simpler to prove that you have a right answer than it is to explain how an LLM got to its answer.
yeah, I think it's definitely an ongoing discussion. Is there anybody
Yeah.
else that we haven't heard from yet? So I saw some other people kind of jump on later. So yeah, all of this, so it's on YouTube, so it's Chemical Q Device, and it's on GitHub too. So I probably have the leading kind of like in the technologies that we're talking about with, drug discovery, medical on GitHub. But yeah, feel free to put anything in chat, and then you can also come on, or you should be able to come on as well. And feel free to ask this is the time to ask, by the way, any application specific questions that you have that you're working on right now, and how you could apply, Gen AI for your medical application. So yeah, there's definitely a lot of stuff going on, but I really think that with Gen AI, it's the Fortune 500 companies, their top form of AI that they talk about, and then the rollout. We're actually having the products, and we're having, the solutions and the answers right now. And now it's going to be on phones. And I did a number of phone experiments. I could get up to about 5 gigabytes on a 8 gigabyte iPhone on a model. It's just going to be a little bit slower. So, but yeah, I think application everywhere. Can you run this technology on phones and, practical utility, iPads, and, even in hospital too. Like if everybody's carrying around an iPad, that's runnable type of hardware, of Gen AI for sure. So yeah,
So,
feel free to put in the chat. Does somebody have something? Go ahead, Noreen.
did you say that you're going to put today's recording on YouTube?
Yeah,
Are you going to
yeah.
put it on
So
YouTube? Oh, okay.
Yeah.
Which
and
number is it going to be? 142, you said, or
yeah, it'll always show up as like the most recent, but
the most recent? Okay.
yeah, so it comes up very easily on mine. And here we go. So I'll put that there. And again, you can go through
Thank
this
you.
again. And I think that like the summary of this is it's application time. It's now to apply advanced technologies into and I tried 3-4 months ago to do drug discovery and GenAI, but it took me 4 months to get to this point, and now I'm ready. But that's just how it goes, right? Like some things you just don't know. Like you have to develop in all these other frameworks and then wind up running on some desired, devices. But yeah, I put the YouTube in there, and there's also, the GitHub as well. I would really check out the Groq stuff because right now it's actually free. It's in beta, and you shouldn't be charged anything, especially if you didn't give him a credit card. So this will also link to the rest of the GitHub. And I think it's amazing technology because I haven't come across anything that fast. I can run a small, say 350 megabyte model on this MacBook at close to 200 tokens per second, or maybe about 150 or 170 words per second. I think that's cool, right? And the other stuff that I'm going to be working on too, because Ron actually asked this question, is about training your own model. And I think there is enormous benefit of being able to get as much of the software, like the GenAI software, into people's hands that need to run data privately. And it's not an option to run any of this, off the cloud, right? You just can't send off your pre-paper submission data, that type of stuff, back and forth. So, but for more specific tasks, right? I'll give you an example. So there's also on LinkedIn right now, I ran Qwen 2, which is a 500 million parameter model. It's really small. Its primary focus is on English and Chinese, and it does others too. And I use this for users across the country. And then so I said, in this specific case, ask a question about technology, and it gave really basic, good results. It's not going to be detailed. Some of them were lengthier, could get up to, 10 bullet points, that type of stuff. And I think to myself, well, I'm just using English. Why should I, why do I need these other parameters, for other things that are more I need for science, like drug discovery and those types of things? And how much context and how much information can I build into a 500 million parameter, just training off that specific data. So the issue is the context. So for instance, Llama 3 8 billion has a lot of English context that, say the Qwen 2 might not. And you're going to lose some of that context, meaning like understanding of the actual drug discovery question, but you want it to also incorporate, new details and facts and answers about, this specific field in medicine. So those are the types of approaches, that, people are taking. Like I said, some have already done, like I know at least 1 or 2 that you just take a Llama 2 or whatever, and now it's up to Llama 3, but they took Llama 2, new, some data set, and then, train it on that one, which is like a good data set to train on, and then train on the original Llama 2 architecture, and then compare the results. So yeah, it's, there's a lot of cool stuff going on. But again, the thing that surprised me most about this week was the sheer number of different types of deep generative models. They call them DGMs across these different 2 papers. And like I said, I was less aware that these are being used because I mostly catch like the LangChain, Hugging Face, and the news about OpenAI, which is generative pre-trained transformer. I mostly catch that buzz. So it was definitely eye-opening. And I'd say kind of looking forward, and this is for me and for everybody too, is just, you got to keep your eyes open, because yes, people get down in a certain technology and it might hit a wall, and then you can't go any further. And then, find out what the challenges, the opportunities, what you could do in your capacity to make things better. So Awesome. Any other questions or comments? So again, if you haven't had a chance to, come on, you can feel free to put it in the chat in this holiday week here. And I would take some time too, with the repository too, is to look at a lot of these, even the Apple one, right? I ran an Apple iPhone Pro, MacBook Pro, 48 gig, it's an M3 Max, and then an iPad Pro M4. And it's cool stuff, right? The app was called, I'll put it in the chat, LLM Farm. And like I said, close to 50 tokens per second on this. And then on the other two, I think the iPad was like 16 and then the iPhone was like 8 or something like that. So the software you're going to be seeing that runs fast in the fall, and as the iOS, kind of churns right now and gets further developed, is likely going to be very like small models that do very good specific tasks. I saw a math model that they have up. And, that'll be that. And they're all just like how you use Siri or whatever, or your Android devices to back up your data. Those similar types of servers, but now are going to be for GenAI to handle the more complex tasks. But you probably won't be sending that information to OpenAI. It'd be like OpenAI software running on Apple servers is what it sounds like. So yeah, the speed component is huge. And like I said, I had some users upload an image, and there was just like if you upload an image on Messages or ChatGPT, occasionally there's just issues with speed, sending it to the server, getting it back, usually sending it to the server, because if you're just returning text, that shouldn't be an issue. But anyways, you can have a big impact just returning really fast responses. And I think that's a good kind of like principle to have in your mind, and combined with really good results on small models and those types of things. But figure in my way, probably a lot of these smaller kind of private models that run, on specific tasks, for the field that I'm in. Any other last questions or comments? I appreciate everybody coming on, taking time on your holiday break here. In the US, it's July 4th tomorrow. But yeah, any other kind of last comments or questions? And I should have the slides up as well. So yeah, this has been Wednesday, July 24th for speed ups for state-of-the-art GenAI for drug discovery. Again, I appreciate everybody coming on. Have a good holiday week, enjoy yourself, but come back working even harder. All right, thank you.